As you see, this is a joint work with colleague Toomas Raus, also from University of Tartu. And in this talk, I will speak about Tikhonov regularization method and situation when we don't know the noise level of the data, then we can use some heuristic parameter choice rule. Well known is quasi-optimality criterion, where the global minimizer of this function is chosen as regularization parameter. But we propose to consider local minimizers. So at first I speak about problem and introduce well-known rules for the choice of the regularization parameter, then about local minimum points of the function what to use in the quasi-optimality criterion, then about algorithm how to restrict the set of the local minimizers, and I finish about choice of a parameter from this restricted set. Our problem is linear operator acts between two Hilbert spaces. If star is exact data, if are noisy data, range is non-closed, kernel non-trivial. And Tikhonov method, if we use exact data or noisy data, have this form as here you see. If we have exact data, we can use such regularizer, but in general we don't know, we use noisy data. And the general problem in application of regularization method is how to use regularization parameter. And I use such denotation. A1 is sum of errors. It is an error for exact data, difference between exact solution and Tikhonov approximate with exact data, and the second is how the noise changes it. And we want to find such parameter for which we have the same order estimate as this estimate. And we choose namely one local minimizer of the quasi-optimality criterion, and we can estimate this constant in this case. A quasi-optimality criterion has uses such function. Use 2 alpha is iterated Tikhonov approximation, and in quasi-optimality criterion, global minimizer of this function is chosen as regularization parameter. And we search the regularization parameter from such a set. So at first we choose alpha 0 and alpha 1 is constant q multiplied by alpha 0 and so on. And the last index is m. And we show that at least one of local minimizers from this set is pseudo-optimal in previous, what we used in the previous slide in this sense. And we will compare the error with rules which use noise level delta. So if noise level delta is known, we can use discrepancy principle where alpha is chosen so that discrepancies between these values. In modified discrepancy principle, alpha is chosen from this equality, and in monotone error rule, alpha is chosen from this equality. Actually, monotone error rule chooses two large parameters. We know that for alpha larger than alpha MA, error is monotonically increasing. So we know that optimal alpha, which minimizes the error, is smaller. So actually, smaller alpha is better, and we recommend to choose estimated, post-estimated parameter. At first, we find parameter from the monotone error rule, and then we multiply it by such constant. And typically, it is much better parameter. Actually, this is such parameter is the best what we know for the known noise level situation. And now about heuristic rules. If we don't know noise level, if delta is unknown. And as said, one such rule is quasi-optimality criterion. And second rule, what we use, mentioned here is Hanke-Rauss rule. Parameter alpha H.R. is global minimizer of such function. Actually, we can use heuristic rules where we minimize product where the first factor is such, and the second is what is used in delta rule. As in delta rules, we find such alpha that this is equal delta. And of course, very well-known rule is L-curve rule. Here, graphs with log-log scales are constructed on x-axis the discrepancy, and on y-axis norm of the regularized approximation, and the corner point is used. Well known is also Reginska's rule, where global minimum point of such function is used. And one can use also a heuristic variant of the monotone error rule, namely if in Hanke-Rauss rule the second factor is function from the modified discrepancy principle, but here instead of modified discrepancy principle we use function from the monotone error rule. As said, we choose parameter from this set, and it is important to note that if we discretize the problem, then actually global minimizer of quasi-optimality criterion function in or Hanke-Rauss function or some other function is 0, and therefore it is important that we search a local minimizer from some interval where here this is here we don't use 0 but some larger value, and here lambda min is a minimal eigenvalue of the matrix of the discretized problem. And actually, if this function has minimizer at lambda min, then this problem do not need regularization at all. And if we choose a parameter from this set, it means that the a priori assumption that our problem needs regularization. We use for the test problems Hansen's 10 test problems, very well known standard set of test problems. Part 32, Fox-Good, gravity, heat, Laplace, Phillips, Shaw, Spike's wing. And we scaled the problems in such way that two norms of operator and right-hand side are 1, and we used discretization number 100. We used also various noise levels in such way, and the noisy right-hand side was constructed in such way. And for each noise level we considered 20 runs, and the sequence of parameters was such that alpha 0, the largest parameter from the set was 1, and the smallest was such, and Q was such. And we used not only standard problems where the smoothness was original, but also smooth problems. And namely, we applied to exact solution operator A transpose. It is the discretized problem. Here are matrices A and transposed matrix. And of course, the right-hand side was modified also in the same way. And lambda min was a minimal eigenvalue of this matrix. And in tables below, we show for different rules error ratios in numerator is error of the concrete rule A, and in denominator is minimum of error where alpha is from this set. And at first, comparison of heuristic rules for case p equal 0. And as you see, the quasi-optimality criterion is in almost all problems very good, but exception is problem heat. Yeah, in the first column, I have written ratios of two consecutive eigenvalues of this matrix in this interval. And as you see in problem heat, this ratio is very large. It means that eigenvalues are concentrated only in certain regions. Hanke-Rauss rule and heuristic variant of monotone error rule don't fail in heat problems, but in average they gave about 2 times larger error than in quasi-optimality criterion. Reginska's rule was good for large deltas. Now about minimum points of the quasi-optimality function. First lemma is that the function in quasi-optimality criterion can be estimated by this error estimation. And remark 2 is that if our largest parameter alpha 0 is too large, it is possible that quasi-optimality criterion chooses it. Therefore, we recommend to take such alpha 0 or to minimize not the function in quasi-optimality criterion, but this function which is multiplied by such factor. And if we use discrete set, then here you see a difference of 2 consecutive parameters. Then here is information that this function is between quasi-optimality criterion function with different alpha. Here is alpha, and here alpha multiplied by q. And if the quasi-optimality criterion function has the same value in many points, then we use for local minimum points, namely the alpha with the largest index k. It means the smallest alpha from this. And the same is R. So we get some set L min, which contains local minimum points. Here you see K local minimizes. And of course, between local minimum points are local maximum points. So we get such sequence. And here is a theorem that if we consider error and consider alphas only from this set, then it can be estimated by values what we used earlier. So it is this inequality shows that this set L min contains quasi-optimal parameter. Pseudo-optimal, I used such word. And we can find also this constant C here in such way. And the second item is about case if the exact solution as a source-wise representation, then we get order optimal error estimate here. It's the same order as best possible order. And now in this table you can see results for this set. And in this column you see best for the best parameter from this set, averages of the error ratios and maximums of error ratios. And here for comparison you see error ratios for rules which use delta. In monotone error rule you see the average was such it is larger than for the best parameter from L min. And for post-estimated monotone error rule, actually the average of these values in different problems is actually the same as here in set L min. And here are results for the discrepancy principle. Here you see cardinality of the set L min. So the set is not very large. In average, there were only 4 elements, and maximum were 10. And here you see in this column constant C, what we get in a posteriori error estimate. And these constants are not large, so it means that parameter from this set is pseudo-optimal. And now about restriction of this set. Namely, we use 2 phases for the restriction. In the first phase, we remove from the set L min local minimizes in interval where the function what we used in modified discrepancy principle decreases only a little bit. This function is monotone, so if we our smallest parameter is alpha m, so the smallest value of this function is this, and we consider parameter from the what we get in modified discrepancy principle when we use instead of this value p times larger, p is larger than 1. We used in numerical experiments p equal 2. And we use also such parameter alpha mtq is minimal from the from this parameter which we get from this inequality, and alpha q is global minimizer of the quasi-optimality criterion. And then we don't use local minimizers with larger parameter than what we used, what was here. So, and we remove from the set L min these local minimizers which perhaps about the second phase is here written. We remove from the set obtained on the first phase these local minimizers for which a function which is used in the quasi-optimality principle for decreasing alpha values has only small growth before the next decrease. So these minimizers are not very essential. So it is formally written down what it means. And so we get a restricted set of the local minimizers. And actually, for this set, we have the same estimates as for the L min without star. So for restricted set, we have it contains also a pseudo-optimal parameter. Here you see is the A1 alpha, A2 alpha was one estimate of A1 alpha of the same order dually. And here you can see how we can find this constant from this estimate. And here you see the estimate for source-like solutions. So this inequality shows that also this restricted set of local minimizers contains pseudo-optimal parameter which has the order-optimal error estimate. And in this table, in this column, you see average of error ratios for the best of local minimizer from this set. And here you can see maximums of the error from the error ratios. And as you see here, this set, restricted set of local minimizers has one or two elements in average only, maximum 4 elements. And this column shows a constant in a posteriori error estimate average equal 5 and maximum 11. And the last column shows percent in which cases this set contains only one element. And as you see, in many cases, it is so. And now, if how we find parameter from this set. If this set contains only one parameter, of course, then we take this parameter. If this set contains two parameters, one of which is the smallest parameter from omega, then we take another parameter. And if this set contains, after possible elimination of smallest alpha, more than one parameter, then we use one algorithm of the following algorithm. The first algorithm A uses parameter from the Hanke-Rauss rule also. Namely, let parameters alpha q, alpha h, A be global minimizers of the quasi-optimality criterion function and Hanke-Rauss function in this interval. And let alpha q1 be maximum from these two values. And we choose largest parameter which is smaller or equal to this. And algorithm B and C are analogical. In algorithm B, we use Reginskas function, namely alpha R is a global minimizer of the Reginskas function on the interval. Actually, in Reginskas function, we can use various values of tau. We used 1. And let alpha q2 be the global minimizer of the quasi-optimality criterion function on this interval. And we choose from our restricted set the largest parameter, which is smaller or equal to alpha q2. And in algorithm C, we compute for the parameters from a restricted set of minimizers ratios, where here you see Hanke-Rauss function. Here is a norm of the regularized approximation. And it can be seen as a rough estimate for the relative error. And we choose for the regularization parameter the smallest parameter from the set which satisfies such condition. For the constant C star, we used 5. And now you see, actually, these three algorithms, A, B, C, gave actually almost the same results. Averages of error ratios and maximums are quite similar in all three algorithms. In previous tables, we used non-smooth solutions, but here we use a smooth solution. And as you see, in this case, results are better, actually. Actually, in most cases, this set L star min contains only one element, and we have no problem how to choose from this set. And if we compare with delta rules, we see that best of local minimizers of L min and the best of local minimizers of L star min, restricted set of local minimizers, they have actually the same average as best delta by best delta rule. And for the restricted set of local minimizers, this average is somewhat larger, but also better than in monotone error rule. It is all.
So thank you very